Hello students, I hope you all are having a wonderful day. So the purpose of this video is to get you acquainted with Chapter R, Section 4, which deals with rational expressions and operations on radicals. So when you hear that word rational, we've looked at rational expressions before, and we've stated that when we utilize the word rational, we are referring to fractions. So in this section, we're going to do a lot of talk and dealing with fractions. So we're going to start out by determining the restrictions on the variable for each rational expression. And so if you look on your left side of your screen, you'll see that I have three different fractional expressions. And I'm trying to identify what exactly is not allowed. So before I even begin, I want to start thinking about a fraction, and I want to ask myself, what can't occur within a fraction? Is there any value that is going to cause an error? And we know that when we're dealing with the fraction, we've talked about the idea of dividing, and we use the examples of Oreos, and we had said if we have no Oreos and we want to divide them among two people, then the answer is equal to 0. So that's okay. 0 is a number. It is a value that we understand. So when we have 0 in the numerator of a fraction, we're good to go. But then we discussed if we have 0 in the denominator. So let's say I got 2 Oreos, but I want to divide them among 0 people. Well, how do I have 0 people? I can't have that. How do I get a solution? How do I tell you how many Oreos each person has if I don't even have people, right? So we said 0 in the denominator causes an error and makes the fraction undefined. So when I look at these expressions that I have, and now they're a little more complicated. It's not just, have 0 in the denominator, but now I got some variables and some expressions. I want to think the problem here is if I get 0 in my denominator. So looking at number 1, I have x minus 3 over x plus 2. And that means I'm going to be plugging in some value of x. I don't care what I get in the numerator. Any value is allowed, and I can be able to solve the fraction. But what I want to think about is what's not allowed, getting 0 in my denominator. So I'm going to take the denominator, x plus 2, and I'm actually going to set that equal to 0. And when I solve, I actually end up getting that x is equal to negative 2. And I'm going to put a little frowny face beside that because it shows me that if I plug in negative 2, that denominator is going to equal 0, and that's not good. So another way to word that is right here. I have all real numbers work except x equals negative 2. So all real numbers are allowed except negative 2. If I wanted to write that in interval notation, I could say all numbers up until negative 2, but not including negative 2, or negative 2, and then all the positive values are allowed. Okay, and again, using parentheses because the value negative 2 is not allowed. So I'm going to continue with that same idea. So on number 2, I see I have a fraction. I don't want 0 in the denominator, so I can set the denominator equal to 0 and begin solving. And the inverse of a squared is a square root, but we recall that anytime we put in a radical, we need to put in the plus or minus. And that leaves me with a solution of x is equal to plus or minus, and the square root of 49 is 7. So again, all real numbers are allowed except x equals positive 7 and x equals negative 7. Now in number 3, I have a monomial, so there's no operation of plus or minus going on. However, there are 2 variables. So if my x is equal to 0 or my y equals 0, this entire thing is going to equal 0. So all real numbers are allowed in my denominator except when x is 0 or y is 0. So how do we multiply and divide rational expressions? It's really nice when we multiply fractions. We actually get to multiply straight across. Our denominators do not need to be the same, so there really isn't much work to do. We're literally going to take 1/2 times 2, and that gets us 2, and we're going to take 2 times 5, and that gives us 10, and then we can simplify, and that gives us 1/5. Now, when we divide, we have a different process called keep change switch. So I want to think about what this says, and I'm looking at this expression right here, 1/2 divided by 1/6. As we continue through this course, you're going to see this written in different ways, but essentially I have 1/2 and I am dividing this by 1/6. When we have what I call fractions within fractions, so we have this fraction on top, and then we have this fraction on bottom, and then we have this entire fraction going on, this is called a complex fraction. And we don't like working with complex fractions. So our goal when we're working with a complex fraction is to try to get rid of it. And when we want to get rid of it, we're going to take our denominator fraction, or it doesn't even have to be a fraction in the denominator, it's whatever is in the denominator, and we're going to multiply it by its reciprocal. So I'm looking at 1/6, and I want to multiply it by its reciprocal, which would be 6/1. So I'm multiplying by 6/1. And we've already learned that reciprocals end up canceling each other out so that I don't have to worry about it anymore. But if I multiply something on bottom, I have to multiply on top as well. And what I would like you to notice is that I end up with 1/2 times 6/1. Well, notice that if I do the process of keep, change, switch, so I'm going to keep this first fraction 1/2. I'm going to change my division sign to a multiplication sign and switch my second fraction to its reciprocal of 6/1. It is the same thing that I got over here on the left. And so essentially all you're doing is you have a complex fraction, and the process of keep, change, switch is the mathematical process you have to go through in order to get rid of a complex fraction. And then I multiply across, on top and on bottom, simplify, and I would end up with my final answer of 3. Now dividing gets a little more complex as I begin to start to work with rational expressions that are larger polynomials. So if I go through and I do my keep, change, switch process here, you see the solution of what's going on. I had a difference of cubes here, so I have gone and expanded that. You'll see I'm highlighting that in purple for you. I've gone ahead and taken, let me switch colors here. I have gone ahead and taken my x squared minus x minus 6, and I've gone ahead and expanded that for you as well. And then I have taken my 3x squared plus 6x plus 12, and I took out a greatest common factor. And then I have taken my 4 minus x squared, which is a difference of squares, and I have expanded that for you as well. I would encourage you to pause this video at this time. Make sure you agree with how I have expanded, and then we're going to continue with our multiplication processes. Continuing with our processes, we notice that we have the x minus 2 on top and on bottom. So we went ahead and canceled that out. We noticed our other polynomials that were alike and canceled those out. And we were left with just this 3 and this x minus 3. And so I've written my final solution here. Now there is a note because we had to do something a little weird here. We ended up actually taking out a -1 if you notice here, because we had x minus 2 and we actually had a negative x plus 2. So by taking out the negative sign, it allowed us to cancel those out, and that's where this negative came from over here. So you just took out a greatest common factor of a negative. Okay. Let's look at another example. Again, I encourage you to pause your video here, work on this on your own, and see how far you can get. So dividing the rational expression, again, remember that I'm going to keep my first fraction. So 6z minus 2, I'm going to keep all over 6z plus 24. I'm going to switch my sign to multiplication. or I should say change, keep change, and switch my fraction, which is the reciprocal. So z plus 4 moves to the top, all over 3. At this juncture, nothing yet cancels out. So I'm going to do my next step in green, and I'm going to start to take out a greatest common factor. And I see 2 in the numerator, and that leaves me with 3z minus 1. And I see 6 in the denominator, which leaves me with z plus 4. And then I have z plus 4 over 3 on the other side. I note that I have z plus 4 in the top and on the bottom, so those can go away. I can then multiply my 2 times my 3z minus 1, and that's all that there is in the numerator. So that gives me my new numerator solution. And I see that I can multiply my 6 times my 3, which is equal to 18. And then I notice that I actually can simplify some more because I end up with 2 in the numerator and 18 in the denominator. And that reduces down to 1 over 9. And so I have 3z minus 1 left in the numerator and 9 in my denominator. And that represents my final solution. We're going to look at another expression here. Again, I encourage you to pause the video and then resume once you have gotten a solution. To give you a little hint, you are going to want to try your best to break down and decompose each of these polynomials so that things begin to cancel out. So looking at my solution, I began here by decomposing each of the polynomials. I then began to do my keep, change, switch process. I then began to see, all right, what values are on top and bottom that I can cancel out. And then I wrote down whatever was left over as my final solution. You're welcome to multiply those binomials back together, but you're not required to. Now thinking about how we add, so moving on to a different operation. When we add, our denominators must be the same. So we are actually going to add what is on top, keep our denominators the same as we move across. So here I've given you an expression where the denominators are the same. So I'm going to bring the denominator over, so 4, and I'm going to add on top. 1 plus 1 is 2. And 2 over 4 is 1/2. But unfortunately, denominators are not always the same. So as you see here, I have 1/3 plus 1/4. So I am going to try to make the denominators the same. I can do that by completing this process that I have listed here, which says to actually multiply your denominators together. Or I can think about what do these denominators have in common. And so the best way I like to think about this is I'm going to write out my fractions. And I'm going to say, what is the least common multiple that 3 and 4 share? And that does happen to be 12, which is the same value I would get if I multiplied 3 and 4 together. The least common multiple and what you get when you multiply the denominators together may not always be the same. So then I asked myself, what did I have to multiply to get from 3 to 12? And that would be 4. If I do it to the bottom, I have to multiply to the top, and that gets me 4. And then to get from 4 to 12, I multiply by 3. If I multiply 3 in the bottom, I have to do that on top, and that gets me 3. Add across, and I am left with 7 over 12. So I've given you another expression here, and now this contains variables. So I'm going to do the same idea. I'm going to think about what is the least common multiple. First, concentrate on just the numbers, 10 and 4. What is the least common value that I can get? Well, 20 is one of my answers. Notice that you could have multiplied 4 and 10 together. You would have gotten 40, which just means you would have to simplify at the end. Then I noticed I have an a and I have an a squared, so the least common multiple would have to be a squared between both. So what did I multiply by 4 to get to 20? I had to multiply by 5. So that means I have to multiply 5 on top. And to get from a to a squared, I had to multiply an a, which means I have to multiply an a on top. So that gives me 35a. To get from 10 to 20, I had to multiply by 2. The a squared was already there, so that's all I had to multiply was by 2. So I'll do that to the top. And then when I combine these answers, they are not like terms, so I will leave it as 35a plus 22 all over 20a squared. One thing that I would like to mention before I move on, the operation that I have done here is addition, and this works exactly the same way for subtraction. So again, going back to complex fractions, because I did want to expose you to a complex fraction that contained a variable, and then I want to move on to polynomial expressions within complex fractions. But remember, we said that this is just division of two fractions, so you're doing the keep change switch, or you can think about needing to multiply by the reciprocal of whatever is in the denominator. When I multiply by the reciprocal, that makes this go away, and whatever I do to the bottom, I must do to the top as well. And now I'm just dealing with a multiplication problem. So 4 times 3x is 12x. 5 times 2 is 10. And when I simplify, I am left with 6x over 5. And that represents my final solution. Looking at this expression, you see that I have polynomials, in fact binomials, in both my top and in my bottom. But I'm going to do the same thing. I'm going to take the reciprocal of the denominator. Those are going to cancel out. And I'm going to multiply the same value on top. And I am left with x plus 5 in the numerator, x minus 4 in the numerator. And I notice that I have a difference of squares, x squared minus 16. So I'm going to go ahead and expand that to its, I'm going to write out its factors, which are x plus 4 and x minus 4. And then I notice I have another difference of squares, x squared minus 25. So I'm going to write their factors, which is x plus 5 and x minus 5. And you'll note that the reason why I did that is because I noticed that I have x plus 5 on top and on bottom, which goes away. And I have x minus 4 on top and bottom, which goes away. So my fully simplified response is everything went away on top, so that's 1 over x plus 4 times x minus 5. And again, you're welcome to multiply those together, but you are not required. All right, looking at another complex fraction. You'll notice a difference here that you actually have a lot of fractions here. You no longer just have monomial terms, but you actually have binomial terms, and that's because you have two terms being separated by your plus and minuses in both your numerator and your denominator. So if you're taking notes in your paper, you would want to write that your first step is to create monomials in both the numerator and the denominator. All that means is perform the operation in the top, perform the operation in the bottom first. Then you will do your keep, change, switch process in order to further simplify your complex fraction. Again, I encourage you to pause this video to try this on your own, and you can resume when you're ready for the solution. So there's a lot on your screen, so I'm going to highlight. We're going to take this step by step. I want to first focus only on my numerator. So I'm highlighting everything on top because that's what I want you to focus on. And I'm actually going to go and zoom in here and really get you to focus only on what's on top. So I have x over 4 minus 4 over x, and I notice that their denominators are not the same. But I want to try to get them to be the same. So I'm going to make sure that there is a 4 in both denominators, and I'm going to make sure that there is an x in both denominators. So my denominator becomes 4x. And I think about, what did I have to multiply in the first fraction? Well, I had to multiply by an x, so I have to multiply the x on top, and that gets me my x squared value. And on the second fraction, I had to multiply by a 4, so that means I need to multiply by a 4 on top, and that gets me my 16. And then my minus sign, because that was the operation that I was doing. So I've now created my numerator expression into one easy to deal with fraction. And then we're going to go and do the same thing, and we're going to concentrate on our denominator. So let's go ahead, we'll do this in blue. So this is the area we're focused on. And likewise, I have 4 and x, so I'm going to try to get my denominator to be 4x. So I already had the 4 here. I needed to multiply by an x. If I do it to the bottom, I do it to the top, and that's 1 times x is just my x. And then I already had an x, so I had to multiply by 4. If I do it to the bottom, I have to do it to the top, and that's what gets me the 4, and I performed my operation of addition. So now I have this entire x squared minus 16 over 4x, and all of that is being divided by x plus 4 over 4x. Okay, so that is my new fraction I'm dealing with. So I am going to keep the first fraction, change the sign, and do the reciprocal of the second fraction. Okay, and instead of showing you the solution, I'm actually going to work this out because it might be easier to look at my writing. So I'm going to start by writing out the factors, x plus 4 and x minus 4 times 4x. So all that's going on in the numerator. And then I have my 4x times my x plus 4. And I note that I have an x plus 4 on top and on bottom. I note that I have a 4x and a 4x on top and bottom. So all I am left with is x minus 4. So you take this really nasty complex fraction that you started with, and you end up with this nice pretty solution of x minus 4. All right, I'm going to provide some other examples here. Again, I encourage you to pause this video. See if you can work through these. I'm not going to provide the solutions for the sake of the video, but they are some practice problems you can attempt. And if you have any questions, don't hesitate to ask. So here's the first question. Again, go ahead and pause it, write it down, try to work it out. Here is the second problem that you can practice, work on, see if you're able to work it out. If not, you're welcome to reach out to me for any questions. Again, I encourage you to pause this video. All right, one other thing that we want to talk about in this section is rationalizing denominators. When we have radicals in our denominator, we cannot call it a rational expression because the denominator is not a polynomial. So in order for a fraction to be considered fully simplified, you don't want any radicals in your denominator, okay? So we are going to simplify by using a process called rationalization. So I have an example here, the square root of 25 over the square root of 3. And we have learned a property that says we can actually take that fraction and separate the radical with each radicand. So square root of 25 over the square root of 3. And I can simplify that to 5 square roots of 3. Unfortunately, because there is a radical in the denominator, that is not considered simplified. So the process of rationalizing the denominator says, okay, we're going to multiply what we have by 1. If I multiply by 1, I've not changed anything, right? We've learned that's the identity property. If I have 5 and I multiply it by 1, I'm left with 5. So we're going to do the same thing here. We're going to multiply by 1. But we're going to show that value 1 by writing the square root of 3 over the square root of 3. So notice I'm taking what's in the denominator and I'm multiplying that on top and bottom. It's the same thing on top, same thing on bottom, so that represents the number 1. And then when I multiply across, I have 5 square root of 3. Then I have square root of 3 times square root of 3, which is the square root of 9. And square root of 9 is just 3. And there is your final rationalized solution. Looking at the second problem, the same thing happens. I don't need to start out by moving my radicals or anything. It's already set up that way. So I'm going to multiply square root of 3 on top and square root of 3 on bottom. So in the numerator, I am left with 6 square root of 6 because my radicands multiply. And I have the square root of 3 times the square root of 3, which is the square root of 9. And the square root of 9 is just equal to 3. And I can actually simplify because I have a whole number on top and bottom that simplify with one another. And I'm left with 2 square roots of 6. I have another example here. So 5 over square root of x. So we are going to multiply by square root of x on top and on bottom. And I am left with the solution of 5 square root of x all over. The square root of x squared is just x, because we know anytime we have the same index value as the exponent on our radicand, they cancel each other out, and I'm left with just whatever your radicand value is, so just the x. Now you'll notice in the second example that I've actually given you a binomial. There's an operation going on. So we are going to have to use something that we call conjugate. So make sure you're jotting this word down because you'll see this happen again. And we've talked about conjugates in this class before. It just means you are going to have the same exact binomial as what is already there, but the difference is going to be the operation. So you see here I have square root of 7 minus square root of 5. I'm multiplying it by its conjugate, which is the same exact binomial, but with addition. And if I multiply to the bottom, I'm going to multiply to the top. And I've gone ahead and worked out your solution for you. So if you would like to go ahead and pause this video and work it out on your own and then see if you agree with my final solution, which is 2 square roots of 7 plus 2 square roots of 5. I have one last example for you. Again, I encourage you to pause the video and then you can see if your solution matches up with mine. I am going to multiply by the conjugate, which is 2 minus square root of 2 to the top and to the bottom. So on top, I have 3 times 2 minus square root of 2 all over 2 plus square root of 2 times 2 minus square root of 2. So that is 6 minus 3 square roots of 2 on top. And then I get 2 times 2 is 4. And the plus and minus for my outer and inner cancel out. And then I am left with square root of 2 times square root of 2 is square root of 4, which is just 2. And this is 6 minus 3 square roots of 2 all over 2. And that is my final answer. I hope that you found this video helpful. As always, please don't hesitate to reach out to me if you have any questions or concerns.